Introduction. It's always nice to receive whatever's warm in Texas at the moment, because as I'm sure you're aware, it's very cold. So if I do disappear mid-talk, it's not that I've gone suddenly shy, it's probably an internet issue. So I'll try and rectify that as soon as possible. So yes, I am Jack Bishop. I'm a postdoc at Texas A&M. And let me see if I can hide this 1 second. Oh, my screen appears to have frozen. Okay, that's not good.
That looks better.
Okay, you can see now. Okay, there we go. So I'm a postdoc at Texas A&M, and as I mentioned, I'm going to be discussing the Hoyle State, and in particular, an experimental effort to measure the direct-decay component with a TPC. So here's a brief overview of the contents of the talk. I'm going to first start by talking about what the Hoyle State is and why in particular we're going to be interested in studying it, before moving on to discuss the experimental apparatus we use for this, the TexAT time projection chamber, explaining about how that works and some past experiments, and then moving on to this new technique that we employed with TexAT, this beta-delayed charged particle decay. And if I have time, I'll touch on a couple of future projects that I'm currently working on. Okay, so let's start off with the Hoyle State. So what is the Hoyle State? So the Hoyle State is a resonance, and it is the second excited state in carbon-12, and it sits just above the alpha threshold. And it is a state that is vitally important for the triple alpha process. So as many of you may know, the triple alpha process is the astrophysical reaction in stars where we take helium-4 alpha particles, and we want to fuse those together to create the heavier elements. So we take these two alpha particles, they fuse together to form beryllium-8, which is unbound by 92 keV. So this is a nucleus that has a typical half-life of 10 to the minus 16 seconds. So we have this constant equilibrium where we're having these alpha particles forming beryllium-8, and it decays back again, and we have this equilibrium. And typically we have about 1 part beryllium-8 to 10 to the 9 parts helium. So as this reaction is going on, there's the possibility that in the meantime, when we have this beryllium-8, a third alpha particle can come in, it can interact with this beryllium-8, and we form states above the alpha threshold in carbon-12. As I mentioned before, the Hoyle state is something that is vitally important for this process. And it's actually through this the presence of this resonance that this overall reaction process is enhanced by roughly 7 orders of magnitude. So if it weren't for the existence of this state sitting at roughly the right energy with the right properties, then all life as we know it may not exist, and our universe may be very boring, because we would never really be able to overcome in a very strong way this A=5, A=8 bottleneck in nuclear synthesis. So once we populate the resonance through this triple alpha process via these 3 alpha particles coming together, one of 3 things can happen. The first, shown on the right-hand side, is that by some sort of decay, we can de-excite from the Hoyle state down to the ground state. So the dominant way for this is sequential gamma decay, but we can also have a small pair production branch. And this happens about 0.04% of the time. Now, the vast majority of times, so over 99.9% of the time, we populate this resonance, and then it decays straight back apart again into beryllium-8 plus alpha particle. And we have to start this whole process over and over again. And you can see that there's actually a third branch, which I've shown here. So this is where the carbon-12 in the Hoyle state can decay rather than a sequential decay through the beryllium-8 ground state and then an alpha decay, and then the beryllium decays into 2 alpha particles. We can directly decay into 3 alpha particles through this 3-body reaction. So you may ask, okay, why do we care about this? So the internal structure of the Hoyle state actually has a very large impact on this branching ratio. So if we want to try and understand a little bit about what the structure of the Hoyle state is, then perhaps this is a good thing to be able to measure. We know that the Hoyle state itself is highly alpha clustered. So this means rather than thinking of an amorphous ball of protons and neutrons, if you look at the intrinsic structure, you can think that there are actually little preformed clumps of alpha particles which are sitting inside the nucleus. And it'd be very interesting to understand exactly how the Hoyle state is clustered in this way. So there are a few different models which are backed up, some by experiment, to how we can describe this type of clustering. So one that is fairly successful is thinking about resonances in carbon-12 in terms of a triangular arrangement of alpha particles. And by making it expand, by vibrating it, by spinning it, we get a whole series of resonances predicted in carbon-12. And we can see that by looking at the energies and the spin parities of these states, it seems to match this D3H symmetry, which describes this triangular arrangement fairly well. If we look at AMD calculations, however, looking at this second 0 plus here, we can see that perhaps this is a bit of an oversimplification. And in fact, it looks like the intrinsic structure of the Hoyle state may be something more analogous to a beryllium 8 plus an alpha a little further distance away. And an idea that was propagated in the early 2000s was, what if we think about the Hoyle state in terms of a dilute gas of alpha particles? So this is a very diffuse structure where these alpha particles are very loosely bound. So this is what we call an alpha particle condensate. And to think about the intrinsic structure of this alpha particle condensate, we want to think about how we're looking at a transition from a fermionic to a bosonic system. So the underlying degrees of freedom are no longer the underlying protons and neutrons, but the alpha particles that are inside of this carbon-12 system. Now, obviously, alpha particles aren't true bosons, they're pseudo-bosons, but as long as we don't resolve the underlying structure by having the alpha particles sitting too close to one another, then they seem to behave like a bosonic system. So this means that we get a very large occupation of the 0s orbital in something analogous to a Bose-Einstein condensate, but instead of a very large number of bosons, we're looking at a very small number, i.e. 3. So this really constitutes a different phase of nuclear matter. And there's been studies looking at when this phase transition actually starts to occur. And you can see that when the nuclear density drops below 1/4 of the normal nuclear density, then this is where this phase transition seems to take place. Experimentally, evidence is so far, let's say, proved inconclusive. So there have been a number of studies looking not just at carbon-12, which is a system of 3 alpha particles which can form this condensate, but you can look at 4, 5, 6, 7, and so on. And I think up to nickel has been studied. And so far, the Hoyle state is the only well-studied candidate state. So let's focus in on carbon-12 if we really want to get a good idea of what exactly is going on and whether this alpha particle condensate idea is a cogent one or not. So the really interesting thing here is that if you think about this very unusual type of matter, you've got this loose gas of alpha particles, and decays to other alpha condensates should be enhanced. So what this really means in practice for the Hoyle state is that if we have this loose 3 alpha particles, then what we'd expect to see is an enhanced direct decay to these 3 alpha particles. You can think of it that they're very loosely bound, so we can essentially just pluck them out very simply one at a time. Whereas if we had something more analogous to this system here, then it's very much a beryllium 8 plus an alpha system. So if we have an alpha condensate, we hope to see an enhanced direct through alpha decay. So that's what we can infer from measuring this branching ratio. Now, this is a branching ratio that has been measured fairly rapidly over the past 4 or 5 years. And over time, there's been a series of concerted experimental efforts which bring it down this limit. And the current limit shows that at the 95% confidence level, this branching ratio is less than 0.019%. So if we start to think about how far we need to improve on this particular branching ratio before we can say conclusively whether this is indicative that the Hoyle state has an alpha condensate structure or not, then a factor of 10 or so would allow us to definitively reject the model. So if this is the current limit, then we have to start to think about what are the underlying experimental limits that these experiments couldn't progress past.
I'm trying to listen to this talk.
Oh, Nick, I think your microphone's on. So all of these experiments either use inelastic scattering on a carbon target, or they use some sort of transfer reaction. And they pick up the decay of the Hoyle state with an array of silicon detectors. Now, the problem here is sort of twofold, and these are two things that you have to battle with. The first one is statistics. Obviously, if we're looking at a very rare decay, then this is something which we need to generate a very large number of Hoyle state decays in order to see these with good statistics. And the second is concerns about pileup. If we have a high beam current so that we are able to see lots of these events, then there may be situations where you have multiple events arriving in your detectors at once. And it's actually very easy to misidentify these direct decays for these pileup events. So we need some sort of new paradigm where we can overcome some of these deficiencies to be able to push down this limit if possible. So that is something that we aim to do with the TexAT time projection chamber. So TexAT is a time projection chamber. So I'm just going to explain briefly for those who don't know how a time projection chamber works. So we have this purple particle here, which is the charged particle, and it's passing through a chamber which is filled with gas. And as it's passing through, it's losing energy and it's producing electron-hole pairs. And by applying an electric field, what we can do is we can drift these electrons that are generated, and we can collect them on a plate down below here. And if we have some form of position sensitivity, then by looking exactly where these electrons are arriving on this plane, we can get a projection of the track. And what we can also do in conjunction is that by looking at the time that it takes, the arrival time of these electrons, we get an idea of what the height is. So using these two things together, we get a full 3D track of exactly what's passing through our time projection chamber. So in reality, it looks a little bit like this. So this is the TexAT time projection chamber. And we'd fill this central area here with gas. Around the outside is what we use to apply the field cage. And you can see we have a large amount of electronics on top, which allow us to read out the electrons which are generated. So in order to get this position sensitivity, we rely on using the so-called micromegas. So the micromega is our readout scheme, and it actually has two functions. The first is what it actually does is it takes the electrons which are coming from the drift region, and the first thing it does is it amplifies those signals. So we end up with a very small number of electrons, but enable to generate a reasonable size signal. So our signal to noise ratio is good for electronics. We want to amplify that. And the way we do that is we have a 128 micron gap, and we apply a voltage of around 500 volts across that. So we get a Townsend avalanche, and one electron produces of the order of 1,000 electrons. So we get a very good signal. And the second thing is that this micromegas itself is separated, and we have position sensitivity in the form of pixels on this. So on the right-hand side, it shows you an idea of what the micromegas board will look like. So the beam comes in this direction following the red. And if the beam doesn't interact with anything, it spends all of its time in the so-called central region. So in this central region, we have pixel pads, which are 1.75 by 3.5 millimeters. And in the side regions, if we have any reaction products which come out from the side, then there's a slightly different network of channeling. So in the side regions, to reduce the number of overall channels that are necessary to cover such a large area time projection chamber, what we need to do is we need to couple together many, many different pixels into strips and chains, which run parallel and perpendicular to the beamline. So this reduces the number of electronics channels needed to something manageable, but we can also still reconstruct our data in the side region. It's just an extra step involved. And as Anna mentioned, there's a concerted effort to upgrade the TexAT detector to Tibet, and this upgrade eliminates this necessity entirely. So one final feature that we have in addition to the micromegas is the use of these thick gems. So these are gas electron multipliers, and they work in a very similar way to the micromegas. We just have two electrodes separated, and we have a large voltage across them. And this just gives us an additional factor of gain for our electrons, which we're then detecting with our micromegas. And these are particularly going to be useful when we're studying very low energy particles, which are the far side of the Bragg peak. So their energy loss per unit length is going to be very small. So we need to get whatever gain we can to be able to see them above the noise. So this is what TexAT looks like overall. So in total, we have a 224 by 240 and a 130 millimeter high area. We have this segmented readout, and all things together, we end up with 1,024 channels. So if we're reconstructing an interaction, then this gives us a position resolution of about 1.5 millimeters in the beam direction. As I mentioned before, we also have these gems, these gas electron multipliers, which allow additional gain. And these are particularly important when we're studying reactions where we have proton recoils, which will have a very small energy loss. The whole thing is tied together with the general electronics for TPCs, or the so-called GET system. So what this does is this digitizes the signal from each of these pads, these 1,024 channels in the micromegas, in 512 time buckets for a 10 megahertz clock speed. This can go all the way up to 100 megahertz, but for this specific study that I'm going to be talking about, 10 megahertz was optimal. And we also have the option of including an ancillary silicon cesium iodide telescope wall, which isn't actually used in this work, but this is where it sits. So we studied a vast array of various things using TexAT. So one of the key things, the key workhorse really is for looking at nuclear structure and exotic nuclei, where we do thick target inverse kinematics. We get some sort of interesting radioactive beam, and we're looking at how it interacts with our gas of interest, usually methane, isobutane, some sort of helium-CO2 mixture. And there's a wide variety of those. We've also looked at direct fusion measurements. So we looked at the boron 8, which is fusing with P10 gas inside of TexAT, and we managed to do this in a fairly model-independent way. And we can also use it for studying transfer reactions. So there's two examples here. What I'm going to talk to you about today is the specific application of TexAT looking at beta delayed particle decay. And this is detailing some work which has been published last year, and hopefully we'll have another publication released soon. So what is this beta delayed particle decay? So this is an experiment that we started in September 2018, and we came off and finished in March 2019. And the idea is that using TexAT, what we want to do is we want to measure both the implant and the decay of a radioactive nucleus one at a time at the Cyclotron Institute, Texas A&M. So for this particular study, what we did is we sent a beam of nitrogen-12 from this reaction using the Mars recourse separator from the K500 cyclotron. We get this beam of nitrogen-12. We attenuate it with an aluminum degrader down to 25 MeV. When it enters the chamber, it passes over an ion counter, which sends a signal to the cyclotron telling no further implants, please. At this point, the radioactive beam then completely stops in 20 torr of CO2 gas. And then what we'd like to do is, once it's implanted, we wait for the subsequent decay of this radioactive isotope. So nitrogen-12 has a half-life of 11 milliseconds. And if there's any interesting tracks which are generated from the TPC, we can then fully record those. At which point we're ready for further events, and we can tell the cyclotron to start sending beams. The thing we're particularly interested in here is we're interested in about 2% branching ratio where nitrogen-12 beta decays, and it feeds states above this alpha threshold in carbon-12. So the final product is going to end up being 3 alpha particles. So what we want to do is we want to populate the Hoyle state in this way. The nitrogen-12 comes in, it's going to populate the Hoyle state, and then we look at the decay to 3 alpha particles. And by really making sure that it's one at a time, then we can be very certain that we don't have the problems associated with pileup that plague some of the previous experiments. So this all pivots around a pretty nifty feature of the GET system, which is the so-called T2P mode, which was used for double proton decay. And essentially it works with 2 half triggers. So the first trigger is the L1A trigger. So this is where the beam is coming inside of TexAT. As we saw in our GIF before, this nitrogen-12 is going to be losing energy. It's going to leave a signal inside of the micromegas, and we can save that. The second trigger is going to correspond to the decay of carbon-12, potentially the Hoyle states. And the way that we have our system set up is that we require this second L1B decay trigger within 30 milliseconds of the implant, or else we say, okay, this isn't going to decay the way we want, and we save that half event to the disk, and we send the next beam through. If we have the L1 implant, then 2% of these, we expect to see these 3 alpha decays, and by making sure that the two correlate with one another, we can really make sure that we're fulfilling our role of doing this one at a time spectroscopy. So we wait for 30 seconds, or if we see the decay in the meantime, then we can send the beam back to TexAT. So let's have a look at what that looks like. So if we first of all think about alpha bound population, we see that our nitrogen-12 is coming from the cyclotron. As it comes through, it passes through an ion counter. It tells the K500 cyclotron to stop sending any more beam. We wait for 30 milliseconds. It's decayed to the ground state of carbon-12, so we're not interested, at which point we can send the next beam through and hope everything's okay. 2% of the time, we should expect to see the alpha unbound population. So same thing happens again. We stop the cyclotron, but now this time, instead of just waiting for 30 milliseconds, what we see is the decay of the excited state of carbon-12 into these 3 alpha particles. And we can save this as our decay event. And what we can do for free also is we can save the time between the L1A and the L1B events. And effectively, then we get a half-life measurement for free from this, as well as some branching ratio measurements. So what do we get when we look at this L1B? So this is an example of a fairly high excitation energy in carbon-12, where you can see really beautifully the reconstruction of the 3 alpha particle tracks inside of TexAT. So that's what we're hoping to look at. So this is what a real event looks like on the left-hand side. So what I've had in yellow is I have the beam, which is corresponding to nitrogen-12. And we can see that where it stops, we see these 3 alpha particles popping out. And what we do for our events is we make sure that the endpoint of this beam correlates with the decay vertex for the Hoyle states. Obviously, there's a small amount of diffusion that is allowed. So this is a fairly small amount, less than 10 millimeters. What we can do then is, so we're looking at all 3 alpha events at the moment, but what we want to do is we want to really pin down those that are populating the Hoyle states. So what we do then is we look at the total energy which is deposited by these alpha particles inside of the time projection chamber. So we've chosen our gas pressure such that these stop well within the region of our TPC. So the full energy signal should be deposited. If we have a higher excitation energy, then due to we're the far side of the Bragg peak, then anything that's higher energy will either escape or it will have a higher energy deposition. So if we look in the blue curve here on the right-hand side, looking at the total energy, then these higher lying states are part of this broad bump here. And by selecting the right energy and selecting events which don't escape, then we make a really nice selection in red on the Hoyle state. So we've selected our Hoyle state. So what we want to do now is we want to work out some way of differentiating between this direct decay component and the sequential decay components. So the first way we can actually do this is we can look at the angle of the 3 alpha particles as it decays.
Jack?
Yes?
What happened to the decay of the 0 plus at 10 MeV? I don't see a bump in your spectrum.
It will be part of this continuum, Moshi. Yes, so that will be high enough energy that it will escape. Yes, but they're all in there. Yeah. So what we can do is we can look at the angles between these particular arms. So if we have a sequential decay, then we end up with beryllium in the ground state plus an alpha particle. And every single time, this 1 alpha particle is going to take roughly half of the energy that from the overall decay. So we're going to end up with 1 alpha particle, which has a constant length. And then depending on the decay direction of the beryllium 8, we end up with 2 slightly shorter arms. So we end up with this characteristic Y shape for sequential decays that we see down here. If we have a direct decay, we can try and understand a little bit about how, if we had such a structure, it would be able to decay. And the preferential decay is where the energy is shared almost equally between the 3 alpha particles. So to conserve the momentum, this corresponds to where we have roughly 120 degrees apart, and we have these equilength shapes. So this is something that look a little bit like this. So what we can do then is we can go through all of our Hoyle events. We have 19,000 of them. We measure the angles between these 3 arms and compare it to what we expect for sequential versus direct. So the sequential locus is shown in magenta here, and we expect the direct events to be lying down here around 120 degrees. And what we can see from the data, which is the histogram behind, is that as we fully expect, basically everything can be described by sequential decay, and we have some sort of underlying intrinsic experimental resolution. So no surprises so far. So we need one other thing to be able to really pinpoint and separate the sequential from the direct components. And the way we do this is using the energy partition of the final state. So the way we do this is through the Dalitz formulation. And what we do is we look at the fractional energy of these 3 alpha particles, and they're basically projected onto this 2D plot where we have 3 overlapping axes. If we have a situation where we have a sequential decay, 1 particle takes roughly half of the energy, and if the decay direction between this decay and the beryllium-8 decay is perpendicular, then the other two alpha particle energies are going to have the same energy but lower. In the opposite instance, if the decay direction of beryllium-8 is parallel to the initial decay direction, then this second alpha particle here is going to get a large boost, and this first alpha particle here is going to end up almost at rest. So we would sit on this particular position of the Dallas plot. And if you go through this, this method, you see that anything sequential will lie on this red triangle here. And then we can think, okay, where do we expect the direct decay components to go? So as I mentioned before, the preferential is that there's an equal energy sharing between the alpha particles. So that's at the center of this Dallas plot here. And what I've shown highlighted in yellow is 1/6 of this. So there's a sixfold symmetry. So what we can do is we can collapse all of our data just to look at this yellow segment here. And this is what's shown on the right-hand side. So once again, we can see that there's nothing particularly surprising. We see a horizontal band around here corresponding to sequential decay, and the number of counts decreases as we go towards the center. So using these two pieces of information together, we want to generate some way to see what the contribution of the direct decay is. So the way that we do that is we formulate a chi-squared for both describing each event as sequential and direct. So we get a contribution from the angle plots and the Dallas plot. So for the angle plot, what we do for each event is we look at the shortest 2D distance on this plot to both the sequential locus and the direct locus. And a similar situation here for the Dallas plot, where we look at the distance, the shortest distance between the sequential component and where the direct components are expected. We can then combine these chi-squareds for a sequential and a direct for each event. By converting this chi-squared value to a p-value, this tells us, okay, if we have an event that is sequential or direct, what is the probability that it will look like this? And the final piece of our puzzle is using a piece of Bayesian inference. So we have a very, very small direct decay branching ratio. So if we have one particular event, which we're not quite sure whether it's sequential or direct, it's much more likely that it's going to be an unusual looking sequential decay than a normal looking direct decay. So what we do then is we essentially build this into a model where the probability that it is sequential is this p-value for the event times by 1 minus the 3 alpha branching ratio, i.e. what the sequential branching ratio is. And we can do a similar thing for the direct, where it is this p-value for direct times by the actual branching ratio for direct decays. And by taking these two p-values over many, many events, what we can do is we can then build the log likelihood function. So what this does is this looks as a function of different 3 alpha branching ratios and says, if this is the 3 alpha branching ratio, what's the probability that your data would end up looking like this? And the results are shown here. So on the left-hand side, we have the probability in magenta as a function of the 3 alpha branching ratio in a log scale. And we have this normalized probability. So what we can extract from this is what our 95% confidence level limits are. And the way we do this is we just integrate across this probability likelihood function and look at where we reach 95% and 5% here. So with a 95% confidence level, we can say that the direct 3 alpha branching ratio is between 0.058% and 0.043%. So the thing that's interesting to note here is that we can explicitly discount these lower branching ratios. And the reason that's important is that says that there is something in our data that cannot solely be explained by a solely sequential decay component. So we're seeing some sort of sensitivity to this direct decay component. And what's really nice about this approach versus previous efforts where they see a similar feature, what we can really do is we can pinpoint exactly which of these events are the ones which are essentially direct looking. And we can look at that event on an event-by-event basis and really say, okay, this is something that looks beautifully direct. It's not a result of pileup. And one of these events is shown here. So you can see that rather than looking like a very elongated Y, there are 3 alpha tracks which look fairly equidistant, and they've got a good angular separation between them. If you compare this to a sequential looking event that's shown down below, you can see instantly that these look very different. So for the first time, we've demonstrated this sensitivity to this direct decay component. And what we can see from this probability distribution is that the most likely branching ratio here is about 0.01%. So this is something that is very exciting. It seems like we've really hit the bottom of the experimental limit here. So what can we conclude from this? So if we say that we have a direct through alpha branching ratio of 0.01%, we can start to think, okay, let's go back to our original question. What does this imply about the Hoyle state as an alpha condensate? And as with many things, there are a couple of complications first. The first of these are contributions from the so-called ghost peak in beryllium-8. So the beryllium-8 is 92 keV above threshold. It's very narrow resonance. And in situations such as this, you find that the penetrability factor as you go higher in energy actually rises faster than the line shape is decaying. So you end up with a second peak in your line spectrum. So even though this can really be attributed to being part of the beryllium-8 ground state, if we see a sequential decay which goes through this so-called ghost peak, it can end up looking like a direct decay component. So in actual fact, the 0.01% is the actual direct 3 alpha branching ratio plus these contributions from the ghost peak. So the actual value is going to be smaller than that. The second is related to considerations where you have strange finite state Coulomb interactions and you have to do boson symmetrization because you have 3 particles in the final state. So we can compare these to some predictions for the direct 3 alpha branching ratio. So a very nice approach is to just take a simple WKB model where you look at the 2 and the 3 body phase spaces, and you look at the 2 and 3 body penetrabilities and compare these 2 values. And if you do this, you get a prediction of about 0.18% for the 3 alpha branching ratio. And this without any assumption of an alpha condensate. Now, this is obviously a very simplistic approach. So if you take a slightly more mature approach where you do a full R matrix and take into account final state Coulomb interactions, depending exactly on what model parameters you use and what you feed into this, you get a very broad range of predictions for this 3 alpha branching ratio, all the way down from a factor of 10 lower from what we see, all the way up to a factor of 100 higher. So it's very difficult from this to discern what your prediction should be. And of course, you can just do a Faddeev calculation, and the predictions for this are roughly in the region of what we expected to see here. And there was an experimental effort looking at the second 2+ state in carbon-12, which is sometimes thought of as rotational excitation of the Hoyle states. And what they did there is they did a similar situation where they measured the direct decay component, and assuming that the Hoyle state and this state have the same reduced widths, they scaled, and this is the prediction that you get here, 0.00057%. So a very, very small fraction. This is a very interesting result. It just leaves the question of whether this 2+ state really is a rotational excitation of the Hoyle state or not, which is an open question, I believe. So the long and short is that we've managed to exhaust the experimental limits with this study, and we're at the stage where more theory is needed.
There's a question again.
Moshi? Yep.
I'm confused. Sometimes you refer to a branching ratio. These are in fact upper limit on branching ratios.
Are you talking about these predictions?
For example, the decay from the 2+, it's not a measured branching ratio, it's an upper limit.
Right, yes, but we're the other side of that limit.
Sorry?
We're the other side of that limit, though.
It's an upper limit. It only has one side.
Yes.
So I don't know. Anyhow, we can talk about it.
Yeah. So yes. So you're saying that from this experiment, you'd expect it to be lower than this value.
Exactly.
Right. But we're already way higher than this anyway. So whether we're at that limit or lower than it is almost a moot point at that stage. So we're really at the stage here where more theory is needed, some more mature models of thinking about how exactly we're going to describe this alpha-condensate, what to expect for a cluster structure, what to expect for this new type of structure. So there's not really any evidence that we've managed to deduce here that suggests that the Hoyle state is commensurate with an alpha particle condensate. And as I mentioned, if there are any theory people out there who have some fancy ways that they can start to look at this, then I'd very much look forward to hearing from you. So this was a collaboration between a reasonably large group of people, and was actually the idea of the 3 people here in bold. And it was very nice arriving at my first postdoc and having an experiment ready to go. And it's thanks to the hard work of the people listed here. So I've just got a short amount of time, so I'd briefly like to just mention the funding for this particular project. So this is the Centaur experiment, and we receive various sources of funding for TexAT, both through the DOE, through the Cyclotron, and through Centaur. So thank you to all those people. And just briefly touch on a couple of the future projects. So naturally, we see that this is a very successful technique. We've shown really remarkable sensitivity to these many body decays using this technique. So what we can do is we can extend this now to look at other systems. And the next on the radar is looking at studying nitrogen-13. So here we implant, instead of nitrogen-12, we implant oxygen-13. It populates states in nitrogen-13. And then these states will decay to both excited states in boron-9 and carbon-12. And we end up with an alpha-alpha-p final state. As if it weren't hard enough to analyze 3 particle tracks, why not throw in another one for fun? And there are some examples here of some simulation works modeling exactly what this will look like as it goes through the various states. So this is something to keep an eye out on the horizon. The second is a very interesting experiment which was run last year, which was looking at neutron-induced reactions with a time projection chamber. And it was very nice to receive some exciting press coverage by Scientific American on this, where they came and chatted to us and learned about exactly what we were aiming to study. So this is where we send neutrons inside of TexAT. Again, we fill with CO2 gas. And by neutron inelastic scattering, what we can do is we populate the Hoyle state once again, and we see the decay into 3 alpha particles. So again, there's some exciting experimental results coming soon with very important implications for astrophysics. So keep an eye open. And the third rather is just briefly talking about this Tibet upgrade, which, as I mentioned, is a collaboration between the Cyclotron Institute and University of Birmingham. And what we're doing is we're moving to a system where we have 84 by 84 pixels, no more dealing with strips and chains, which makes the analysis a little bit nicer. And what we aim to do here is, for the first time really in nuclear physics, is to use these resistive micromegas designs. And what we have here is we have a DLC coating on top of our micromegas. And as the charge arrives from the tracks, what it does is it deliberately disperses these charges, so it spreads across many, many paths. And the real advantage of doing this is that by looking at understanding exactly how these charges dissipate, what we can actually do by putting it across many paths is we can get a position resolution that's many, many times smaller than the size of the pad itself. And we can get position resolutions we expect down to around 200 micron. So when we're looking at thick target inverse kinematics techniques, this is very important indeed, as this is part of the driving factor towards our overall resolution for excitation energy. So with that, I'd just like to conclude overall. And hopefully you garnered this from the talk, but TexAT is a general purpose TPC capable of measuring many different reaction mechanisms. And this beta-late charged particle decay in TPCs allows for extremely high sensitivity measurements of few body decays. And that for the first time, we've managed to demonstrate this sensitivity to the direct decay component. But more theory is needed, but there's so far no evidence that support the postulate that the Hoyle state itself is an alpha-condensate. So I'd like to thank the organizers for giving me the opportunity to talk, and I welcome any questions. Thank you.
Okay, thank you, Jack, for a really nice presentation. Are there any questions or comments?
I'm raising my hand. Jack, first of all, it gives me joy to look at your data. Congratulations.
Thank you.
This is a beautiful, powerful tool. No question about it. I'm just wondering, for other experiments, what's the highest rate that your TPC can to collect data?
So we've done some experiments where we're looking at incident rates of 10 to the 5, and it's really at that point we start to see phase charge effects. So again, this is a function of exactly what the energy, what the Z, what the mass is, and also what the gas is, for how quickly we can essentially drift everything out of the way. But I would say no more than 10 to the 5.
10 to the 5 is quite impressive.
Yes, it's it doesn't have the shortcomings of some of the older TPC methods. Yeah.
Good luck to you. Thank you.
Okay. Any other questions? You can raise your hand or just unmute yourself. You can also type into the chat and I can read out the question to the speaker.
So I'm George Bird. Whoops, I muted myself. Yeah, very interesting talk. I just want to point out another Japanese theory paper that does a study of all three mechanisms for producing the Hoyle state in an astrophysical environment. And maybe their technique could be useful, so you might want to contact them. I'll put the citation on the chat.
Okay, great, thank you.
Okay, any other questions, comments for Jack? Philip, I can see your hand up. Go ahead and unmute yourself.
Hello, can you hear me?
I can hear you, yep.
Great, thanks. So I have two questions. I think one of them is stupid, but you mentioned about the beryllium 8 ghost. Is there any chance of seeing the direct decay from the ghost of the Hoyle state? Because that's a bit higher in energy. I don't know if it's easier to see or if that just wouldn't work. But...
Right, so that's a good question. So part of the problem there is that there are these higher lying 0+ states which are very broad. So the ghost of the Hoyle state is going to be immersed in those, but yes.
Oh, okay. And the second of them is, you mentioned about what you'd seen as the direct decay, and then there was the conflicting signals from the decays through the beryllium 8 ghost, and I wasn't sure how those are distinguished. So yeah, I think I missed that.
Right. So you can end up with a decay. Let's say it's direct looking, and it could either be from the beryllium 8 ghost peak, or it could be a true direct decay. And the difficulty is that everything, the energy partition, the angles, whatever, are going to be identical for those two. So experimentally, you can't disentangle those.
Okay. Thanks.
Thank you.
Okay. We still have a few minutes if there are any questions. Looks like you, oh, okay, there's a question. Caitlin?
Hi, first, that was a really nice talk. I had the sort of same question as Phil about the ghost state, but have you had any discussions with theorists about if it's possible to model the population of the ghost state?
Right, so some of these do actually explicitly take this into consideration. And again, it's one of those things that exactly what you put into that model. So this R matrix plus this final state Coulomb interaction does take into account the ghost peak. But it's not really at the level where we can definitively, we're spanning several orders of magnitude here. So it can be put in, but exactly how you treat that in conjunction with everything else is just not really being pinned down yet.
Sure, thanks. I had another like frivolous question.
Go for it.
I'm just curious, how many events did you have roughly that looked like direct decays in the end?
So we had 9 that looked direct.
So you can really look at all of them.
Yeah, which is really nice in this way. And for those that look most suspicious, I went through and I if something wasn't fit well, I went through every single one. I was going slightly mad at times and made sure that it was really what we thought it was.
Thanks.
Okay. I see no more questions in the chat or no more raised hands. So let me thank our speaker again. And before you guys run away, I'd like to advertise our next seminar, which will be on March 4th. And Samuel Henderson from University of Notre Dame will tell us about his measurements of Be2 values in light radioactive nuclei. Thank you very much.
Thanks, Anna.